Hi, my name is Shahnawaz. In last lecture, we proved that the fundamental group of a circle is actually isomorphic to the additive group of integers. Now, in this lecture, we'll prove a well-known application of this result. I mean the fundamental theorem of algebra. So it states that a polynomial equation, say z power n plus a n minus 1 z power n minus 1 plus so on plus a1z plus a naught equal to 0 with real or complex coefficients. See, this is of degree n, which is bigger than 0 with real or complex coefficients. Has at least one real or complex root. Now we'll prove this result in steps. So we'll start the proof, and in step 1 we consider a map. So consider the map, say f from the unit circle S1 to S1 given by f of z is actually z power n, where this z is a complex number, and mod of z is equal to 1, i.e. this z is a point on the unit circle. So one can note here this f is a continuous function, being a polynomial function. So clearly f is a continuous function. So we show that now f being a continuous map, this f will induce a homomorphism between the fundamental group of S1 and the fundamental group of S1. I mean, so since f is continuous, now what we will prove? We'll prove that the induced homomorphism f star from. So we show that in the induced homomorphism f star from the fundamental group of S1, say it is visible point B, to the fundamental group of S1 visited B. So this is the homomorphism of fundamental groups. Is injective, where this B is some point on the circle, say B is the point 1 0. Now to prove this f star is injective, let us consider a standard loop on the circle, say S1. So let P naught from interval 0 1 to S1 be a standard loop. So this is a standard loop in S1 given by this P naught of S is e to the power 2 pi I. Let's call this Z here, or let us call this S here. So this is actually called cos of 2 pi S sine of 2 pi S. Now one can note that this P naught being a loop, so the homotopy class of P naught is actually an element of pi 1 S1B, because when we put um, S is equal to 0 here, we get the point B. So note that the homotopy class of P naught is the element of the fundamental group of S1 based at point B. Now let us see how F star behaves at this homotopy class. So now F star of the homotopy class of P naught is actually the homotopy class of F composite P naught, where F of P naught of S this is F of e to the power 2 pi is, and this is e to the power 2 pi 2 n pi s 2 n pi is, which is same as cos of 2 n pi s sine of 2 n pi s. Now here we have the covering space R of the unit circle S1. This is the covering map here, and we have a loop, I mean a path from interval 0 1 to S1 given by given by F composite P naught. So then by path lifting property, this path in S1, this is being lifted to a path in R. So suppose this is being lifted by, so suppose the lift of this composite path here is Q. So since R is the covering space of S1, the loop, the path F composite P naught, this, so the loop on the path F composite P naught in S1, so is lifted to the path say Q from the interval 0 1 to R given by, so Q takes the point S to NS. Now, why this is so? Because mm, the P naught is a standard loop on S1, on in S1, and F composite P naught is this loop over here. So this loop, this travels around the circle n times. So uh, mm, so this Q will take this S to NS. The reason is that the fundamental group of S1 is the group of integers. So this happens in, so this happens in the covering space R. Again, since the fundamental group of uh, S1 based at B is isomorphic to the group of integers, so under this homomorphism, the homotopy class, I mean the class, the homotopy class of the loop f naught, f of p naught composite corresponds to the integer n. So under this homomorphism, uh, the homotopy class of the loop f composite with p naught corresponds to the integer n. In Z, whereas the whereas the homotopy class p naught, which is an element in pi s1b, corresponds to the integer 1 in Z. So if this loop, I mean this p naught corresponds to 1, then it is left in R corresponds to the integer n in R. So this shows that the map f star from pi 1s to pi 1s is basically the multiplication map, I mean the multiplication by n. So thus the map f star is basically the multiplication map, I mean the multiplication map by n. So this is the multiplication map in pi 1 s1b. So one can understand this from this diagram. So we have the fundamental group of S1 based at point B, and then we have the map F star. So this is map from pi1 S1b to itself, and from this group over here to Z we have an isomorphism. Similarly here we have an isomorphism, and if the loop P naught in this group corresponds to 1 here, then the image of this loop, this element over here, that is the homotopy class of uh, F composite P naught. So this corresponds to the map N here. So this map is actually the multiplication map by N, and this map is always injective. So this, so since these two are isomorphic and these two are isomorphic, so this F star has to be an injective map. I mean, because this map is injective. So hence F star is injective. Now let us move to step second. So in this step we define a map. So define a map so this map is given by, so define a map G from S1 to the punctured plan. I mean the plan R2 minus the zero element by G of Z is Z to the power N. So we'll prove that the map G is null homotopic. So we will prove that the map G is null homotopic. Now one can note that, so note that the map G is actually the map J composite F, where F is a map defined in step first, while F is the map defined in step first. So in step first we define F from so we define the map F from S1 to S1. So that is, if we have S1 here and just like this, so if we have S1 here and here we have again S1, then this is the map F, and this J is actually the inclusion map, whereas the map J from S1 to the punctured disk 0 is the inclusion map. So from S1 to R2 minus 0, this is the map J. So one can note here this punctured disk already contains a copy of S1. So this J is simply in the embedding of this S1 into this punctured plane. So this composite map G composite F will be a map from S1 to the punctured plane. So one can note here this G is continuous because the integral map J is continuous and the map F is continuous. So G is continuous. So clearly G is a continuous map since F and G are both continuous. Also, since S1 is the retractor of R2 minus 0, so let us move to page second. So also S1 is a retract of the puncture plane because we can, so if this is a puncture plane, so this is a puncture plane over here, so this 0 has been removed, so we can, so this plane already contains a copy of the unit circle, so this is the unit circle over here. So we can define a retract of R2 minus 0 to this circle S1 by taking sorry, by taking the points on this line to move over here and these pointers to move over here. So this is the retract of this punctured plane to the unit circle. So this S1 is a retract of uh, the punctured plane. Therefore, the map, so one can note here this J is a map from S1 to punctured plane. So since this J is continuous, this J will induce a homomorphism from phi S1 to the fundamental group of this thing. But the fundamental group of the punctured plane is same as the fundamental group of its retract, which is S1. So as we have shown above, the map F star is injective, so G star is obviously a homomorphism. I mean this, sorry, this J star will be injective as well. So therefore the map, I mean the induced map J star from S1 to the punctured plane is injective. Also the map F star is injective as shown in step first. Hence, so therefore the map G star, since G is a map, continuous map from S1 to punctured plane, so this will induce a homomorphism G star from S1 to R2. So not S1, this is pi of S1 here. This is again pi 1 of S1 to pi 1 of R2 minus 0. So this will, where this G star is same as um, this is same as F star, sorry, this is same as J star composed with F star. So where G star is a map from the fundamental group of S1 to the fundamental group of the punctual plane R2 minus 0. So given as, this map is given as G star is same as J star composed with F star. Now F star being injective, J star being injective implies this G star is also injective. So G star cannot be null homotopy, because if G star is null homotopy, then G star will be a trivial map, and the trivial map is not injective. So then G star, so this thus G cannot be, thus G cannot be null homotopic for if G is null homotopic, then G star is a trivial map. And hence G star cannot be injective. So we forgot here to write, therefore the map G star from this given as is injective. The reason is that F star is injective and J star is injective. So this proves the step second. Now we move to step third. Now in step third, we will prove the theorem. We'll prove a special case of the theorem. So in this step, we will prove a special case of the theorem. So given a polynomial equation, say z power n plus a n minus 1 z power n minus 1 plus through plus a naught equal to 0. Let us call this equation star. So we assume that the sum of absolute value of the coefficients of this equation is less than 1. So i.e. we assume that absolute value of a n minus 1 plus absolute value of a n minus 2 plus so on plus absolute value of a naught is strictly less than 1. So this is what we assume, and show that the equation in star has a root in unit ball b2, and show that the equation in star has a root in the unit ball B2. Now we again assume on contrary that the equation in star has no root in the ball B2. Assume it has no root. It has no root in B2. Now B2 we mean a close. We mean the unit ball. So this is B2. So if this is the case, then we can define. So then we can define map, say theta from B2 to R2 minus 0 by the equation theta of z is z power n plus a n minus 1 z power n minus 1 plus so on plus a naught. So since this equation has no root in the unit ball B2, so this expression is no while 0. So hence this theta is a well-defined map. So this theta is a map from the unit ball B2 to the puncture plane. This is the map theta. Now we restrict this map to the boundary of the unit ball, I mean to the unit circle, and we call that map the map H. So let H be the restriction of theta restriction of the map theta to S1. That is, this H is actually theta restricted to S1. I mean, we restrict this theta to this boundary. So its boundary is S1. So we get a map H from S1 to the punctured plane. Now, since theta can be restricted to the S1, we can extend H to the map theta. So since H extends the map, since H extends the map of the unit ball into the punctured plane. So therefore the map is null homotopy. So we can extend this map H to whole ball. That means we can this map H is going to be homotopic to the constant map, i.e. the map will be null homotopic. Now let us define a map. So define a map, say f from the unit circle cross the interval 0 1 to the puncture plane by f of zt is the expression z power n plus t times a n minus 1 z power n minus 1 plus so on plus a naught. So one can note that the map f is continuous because it is a combination of the polynomials. So note that f of zt is no while 0 because this expression cannot is not equal to 0 for any value of uh, z. So this is not equal to 0 for all z in s1 and t in the interval 0 1 because the reason is that because if we take the absolute value of f of zt, it is equal to the absolute value of zn plus t times a n minus 1 z power n minus 1 plus so on plus a naught. So this is less or equal to z power n minus t to the t times a n minus 1 z power n minus 1 plus so on plus a naught. The reason is that and the absolute value of a plus b is less or equal to absolute value of a minus absolute value of b. So this is further less or equal to absolute value of z power n. So this is minus times. So since t is in the interval 0 1, so we can take t outside of the mod and then we can use the triangle inequality. So this is same as mod of a n minus 1 z power n minus 1 plus so on plus mod of a naught. Now since this z belongs to the unit circle s1, so this is not less, this is bigger or equal to, because over here this is bigger or equal to. So this is same as, so this is same as uh, so this is equal to 1 minus t times the expression mod of a n minus 1 plus so on plus mod of a naught, and we have assumed that this expression is less than 1, so hence this expression is bigger than 0 because t lies in the interval 0 to 1. This is always positive. So clearly f is continuous. Also note that mm, if we restrict z to 0, so we are giving t, we are putting t to be equal to 0, so we get z power n, which is same as g of z. This is for all z in S1, and f of z1, this will be the expression z power n plus a n minus 1 z power n minus 1 plus so on plus a naught, which is called uh, h of z. So this proves that the map G and H are homotopic. But uh, among these maps, one of the maps is null homotopic and other is not. So this gives us a contradiction. So hence G is homotopic to H. This gives a contradiction, since the map G is not null homotopic, whereas the map H is null homotopic. So these two maps cannot be homotopic, but we have proved these two maps are homotopic. So that means our hypothesis is wrong. So hence the expression in star, the polynomial equation, has a root in B2. So therefore the polynomial equation z power n plus a n minus 1 z power n minus 1 plus so on plus a not equal to 0 has a root in B2 when the when this is true. Now finally we prove the general case in step 4. So we have the step 4 here. So now we prove the general case. So given the polynomial equation say z power n plus a n minus 1 z power n minus 1 plus so on plus a naught equal to 0, call this equation first. So let us choose a real number. So let us choose a real number r, and let z is called yr, or r times y. Then we obtain the equation r y power n plus a n minus 1 r y power n minus 1 plus so on plus a not equal to 0, or take r outside, we get, take r to the power n outside, we get a n minus 1 by r y power n minus 1 plus so on plus a naught divided by r equal 0. Now if let us call this equation second. Now if equation second has a root, say y is equal to y naught, then equation first has the root z naught, which is equal to r times y naught. Now we choose r such that so let us write this down. We we choose r such that mod of a n minus 1 by r plus mod of a n minus 2 by r. This is r here, this is r power n, so this will be r square here plus so on plus a naught divided by r power n is less than 1. Then by step 3 the equation in second has a root, and hence the equation first has a root. So then by step 3 equation second has a root, and hence equation first has a root. So this proves the fundamental theorem of algebra.